Hi Year 12s, welcome back to the last half term of the year, and I'm guessing at some point this week we're going to find out what the plans are for being in and face to face. Since I don't know anything definite, I'm not going to share anything with you, and I'm sure we're going to find out, but hopefully, fingers crossed, we will actually be meeting up as a group in very soon. So back to the mechanics. And there'll be two of the Year 13s. Becca and Sam, you might still be watching this. If you are, welcome back. And we're going to look at Chapter 5, which is Work, Energy and Power, Chapter 2. So by all means, be reading that online as we're going through it. Or, no, actually do have that up on the screen. So it's Work, Energy and Power, Chapter 2. And they split the book into what happens if a force is not constant? What happens if we've got a force which is a function of x? What happens if, as position changes, the force changes? So the force not constant. That's the first part of this chapter. Now notice what we're not going to consider is, we're not considering that force changes with time, okay? We're not considering that. We're considering force changing with displacement in this chapter. The other thing we're going to look at later in the chapter is what happens if the force is acting at an angle to the direction of travel. Okay, so we have talked about the work done being force times distance, but what happens if the force is at an angle to the direction of travel? Will be part of this work. That's what they're going to call the force being oblique. You might remember we touched on the idea that force dotted with displacement would give us an answer when we're in the vector notation. Things we should refresh our mind about before we go any further. Work and energy both have the same units, which are joules. Power is the rate of doing work. Work and energy were largely interchangeable. And the other thing we should say about work and energy and force and displacement, some of them are vector quantities. Respect the vector, underline them. Work and energy, on the other hand, are not. Okay, which is why one of the reasons I was justifying we could say that would be a good use of this, a vector product, a vector dotted with another vector but giving a scalar answer. We can use this concept too. So what we're going to do, the first thing we're going to look at is, so if that's the first thing and that's going to be the second thing, the first thing is that we're going to say that work done, if we know the force as a function of x, we can integrate it with respect to x using limits of the starting and finishing displacement. That will give us the work done. And it's a very, very common step to go from where a force or something is constant, we can do force multiplied by displacement. As soon as we find we've got a varying force or a varying velocity, etc., we can turn that multiplication into an integration. For those of you who think, yeah, integration, we might also be considering, let's say we could plot a graph of force against displacement. The area under that graph will be the work done by the force while moving from here to here. Before we do a couple of examples, you can see I wasn't being very brave. I needed to do some notes for myself before I just launched into this. But hopefully I'm going to be brave and do the next examples about it. What forces are a function of x? Or just a couple of examples are gravitational attraction, when we're talking about the planets, when we're talking about the solar system, we find that the gravitational attraction is an inverse square law. And it would be nice to say that it's in an opposite sense to the displacement. And also tension. I don't mean awkwardness in a social situation here. I mean tension as in if you pull a string. I should actually have a stretchy string here, but I haven't got that prop. Imagine stretching an elastic band and letting it go, or let it go too quickly. We find that the tension in a stretched string or spring is proportional to the stretch. But again, it's in an opposite sense to the displacement. So there's two examples of where we might use this idea. Work done is now the integral of force with respect to displacement. So if we have a look at, let's see if I'm going to go work example 5.1, 5.2 and 5.3, and then there's only a very short exercise. Now, for those of you who just weren't keeping up, I know one or two didn't, let's try to get that done before we do Hooke's law and thing on Thursday. So you can write the examples down. I'm just going to go through them. Work done by a force of 8x plus 15 newtons. Right, so that's the force that is expressed as a function of x. Yeah, the force is expressed as a function of x. As x increases, the force is increasing. Okay. Right. That displaces an object from 2 meters to 5 meters. The work done by that force is the integral between 2 and 5 of 8x plus 15 with respect to x. Don't forget the with respect to x bit. I'm just going to the other end of the table to get my calculator. For being lazy, it might be if the next examples are harder. We've got the integrating button on the calculator. Let's remind ourselves we can do this though. Shout if you see any mistakes. 4x squared plus 15x between 5 and 2. So that's 4 times 25 and 15 times 5. So that's the 5 put into both of those. Take 4 times 2 squared, so that's 4 plus 15 times 2. Right, you probably not wanting to see me do this. Let's do all that in one go. So that's 100 plus 75. I really am lazy. I should have done that in my head. Take 16 plus 30. 16 plus 30. 129. 129 joules. Okay, so that's the first example. Worked example 5.2. A car, let's just line off. A car of mass 1,020 kilograms moves from rest. The driving force is constant, but the resistance is modelled as, so for whatever reason, the resistance increases with displacement and it travels 120 meters. Perhaps I should be using X there, really should be, shouldn't I? Right. Work done by the driving force and the work done against resistance. Okay, wants to separate them out. Work done by the driving force. That was constant. So it's just going to be force times displacement. The chance of me getting that right in my head is very slim. So 216 kilojoules. Okay. Work done against resistance is integrate x squared upon 8, the force, between 0 and 120 with respect to x. So into x cubed over 24, we put 120 and 0. That's going to be quite a big number, isn't it? So 120 cubed divided by 24. Wow. 72,000. Always check that 0 gives 0 here. If that had been e to the x or other functions, we wouldn't get 0 here. So I'm going to make sure, always double check it goes, double check that number into that, particularly if it's 0. So 72 kilojoules. That's what we want for part A. Find the speed of the car. Right, the speed of the car. We're looking at this balance between work done and energies, okay? The total work done will be the change in energy, the increase in kinetic energy will be the work done by the driving force, take the work done against the resistance. Some way of expressing, you know, there's a balance. So the work increase in kinetic energy is the work done by driving force, take work done against resistance. Why is that going to help us find the speed? Because the kinetic energy is half mv squared, half mv squared is 216,000 take 72,000, which is going to give us that V equals, just running out of space, we're going to do it all in one go. So we've got 216 take 72 times 1,000 is that, take that. Double it to get rid of the half, times by 2, divide by the 1,220, 1,020, 4800 over 17, square root that, which is 16.8. 16.8 meters per second. 3 sig fig really, book? 2 sig fig, 3 sig fig, 2 sig fig. Personally, I think, well, 2 sig fig or 3 sig fig's fine, isn't it? 4 sig fig, 5 sig fig, not so good. So what have we got there? Work done by a force, work done against the force. The difference in them will be the total change in the energy. Notice that somewhere it told us it was a horizontal surface. So we have to, no consideration, no need to consider GPE. Right, let's have a look at 5.3. There, that's my new graphic noise. Object is moving in a horizontal straight line. Right, so I've actually read that more carefully this time. So the next example, something's traveling in a horizontal straight line, so no need to consider, no GPE, because it's just traveling horizontally, against a resistant force that's directly proportional to its distance from the starting point. So that resistive force is going to be K times X. the work done against resistance between 0 and 15 meters is 337.5 kilojoules. So the work done against the resistance, which is not constant, will be the integral of kx with respect to x between 0 and 15. That's equal to 337,500 joules. Okay, so integrating that between 15 and 0 gives that. So kx squared over 2 between 0 and 15 is that. Notice that 0 going into that again, so that lower limit will give 0 there. So we've got k times 225 over 2, take 0, is 337,500. So let's work that out. 337,500 divided by 225 multiplied by 2 equals 3,000. K is 3,000. What are the units of K? Since F is a force, K must have units. That. It's interesting, isn't it? F of x is kx, and there weren't any units here, so they're suggesting K must carry the units. What an odd question. I might have to think about that. Must carry the units. N. Right, I'm just going to show you something hopefully you're going to be impressed by in terms of this last question. I think most of you have got these. I want to say something about that solve n business. If you go to, in the normal menu one, if you go to option and calc, one of the options is this thing solve n. Press that. It's a function which solves any problem. Now, just because what we're trying to find is a value here doesn't mean we can't use this solve n business. So notice that in solve n, one of the options is the integration, first differential, second differential. So I'm going to press integrate. Now, what I'm trying to find is the k. I'm not sure if there is a k. I'm probably wrong. I'm just going to use the first letter A, and then on that button there I can also use x, because it has to be x with respect to x. Keep going that way, and I can put the lower limit in, 0, and I can put the upper limit in. Now notice, I mean, if it was one of the limits you'd have finding, you'd simply put a letter there. So 15, keep coming that way. The equal sign is shift and decimal point, and we know that that equals 337,500. In the solve n, the way to do it is you then put a comma and you say what letter you're trying to find. I don't know if that means you can put more than one letter here, because the x refers to the dx, but I'm going to say the alpha A. Now, usually when I've done this, I found that I needed to put a comma and a starting value, and a comma and a finishing value. Now, we happen to know that the answer is 3,000, and I don't think I'd have guessed to go as far as 10,000. But what I found is, if you just say you're solving it for A, and close the bracket now, then press execute, it thinks, warning, more solutions may exist, press exit, but the answer is 3,000. Now, this is a relatively simple integral, isn't it? It's just a linear one. You could play about and find out how complicated it is. it is interesting watching one of these really powerful calculators actually having to think and slow down. As I said before, on some of the trig, it will solve anything, basically. It will solve anything, just the more complicated, the longer it takes to think. When I've used it before, I thought you always had to put a comma and a starting value and a comma and a finishing value for the trig problems. So you might put between 0 and 2 pi solving a trig one. So if I press execute now, warning solution, more solutions may exist because I'm only looking between 0 and 10,000. It's giving the same answer, isn't it? Right, enjoy that. So in 5A, there's only 7 questions, and then we can look at Hooke's law on Thursday. Right then, this half term, hopefully we're going to be in together relatively shortly. In the meantime, ask me questions. Right.